Okay, so the fundamental theorem, two versions. So needless to say, it is uh, very important for the course. Um, so it is fundamental, but I wouldn't say that like it might sound like the whole everything relies on it. It's not really true. It just brings things together. And seemingly unrelated things suddenly become together one, and that's the meaning of the fundamental theorem. So two things defined through limits. On one hand, tangent lines, derivatives, and on the other hand, Riemann integrals as limits of Riemann sums and the areas. And then they turned out to be related to each other in a very profound way, and not just say they're not the same. They are in a way the opposite, and that's what makes it interesting. So that is the foundation, not the foundation, but rather the kind of a bang in the end of the course, closer to the end of the course, and so that we know it is one thing, calculus, not just facts all over, but rather something theory that is have some kind of a compact representation. And if you want to study or try to remember calculus, well, start with fundamental theorem, because everything that is important is here. So both integrals and derivatives are here, and if you can understand them if you go back to the definitions, and then now you see how they are related. Furthermore, the second part is computational. Okay, so or rather, not second part, second version, it's the same statement, but now it is about how to compute integrals, how to compute areas, and a lot of other things that are integrals. So a lot of things will be, especially in calculus 2, we'll get a bit of that, but a lot of integrals are interpreted, a lot of things, important things, are interpreted as integrals. So to begin with, what we have done already, and now we can compute, are naturally the areas. Okay, so the areas to begin with. Okay, so the area, curved area, we can compute it as long as, so limitations should be also understood. The function might be so complicated that we're unable to compute its integral. But a lot of things we can handle. Okay, so the areas, so it's pretty much geometry. And then the other thing that we have seen is the, in fact, that what we started with, number one, will be the displacement. So I want you to appreciate the difference. That's two things seemingly unrelated to each other as far as the real life is concerned. Computing areas of curved figures on one hand, and on the other hand, understanding the displacement of your motion whenever your velocity is known. So you integrate velocity, you get displacement. If that function is velocity, if that function represents simply the height or the edge of that object, then you'll get the area. Okay, so two very unrelated things, and that's typical for mathematics. So every concept has so many things inside of it, and has been, and then there will be more. Okay, so new things appear in life, and they found to be just manifestations of certain mathematical concepts. So these are the two main things, and so to keep in mind. Both of them are, I suppose, equally important. The displacement is easier to connect to the derivative. So these are interpretations of the area. I'm sorry, of the integral. The main two interpretations. The areas are harder to connect to tangent lines, and it is actually a bit of a challenge to what I tried to. When we went into this explanation of why the derivative of this area function gives you the, here it is, gives you the function itself. So you have a function, you build the area function like this. You see the right edge of that region over there in purple moves, and that creates a new function defined right on left, and but then somehow the derivative of that function gives you the height. Well, so there's a certain challenge. On the other hand, this interpretation is really no challenge. The displacement velocity location is what we started with. So, but there will be more. Anything related to the one that I want to point out, it is long term very important, is the how should I put it, the mass. Okay, so this is the interpretation. So it is called the linear density. So you have an object of non-uniform density, say made up of two pieces of alloy, maybe they merge together but not quite, and so the density might be changing from one to to the end, and the continuously. Okay, so these dots indicate the density. Okay, so and then the question is, could we find the mass or the weight, if you prefer, of the rod. Okay, so and the answer is it's once again the integral. Okay, so density is say y equal f of x. So for each location you put x-axis here. For each location there's a density at each point, and then the mass weight is equal to the integral from a to b fx dx. So if this is a, this is b. That's how the problem is solved. So as you can see, you get the third interpretation of the integral, and then there will be more, and then there will be, for example, the center of mass of an object and things like that. So related to this. Okay, so so that's the value and the place of the theorem in the large scale. In the theory of calculus. Now here, more formulas, so it probably makes sense to have a couple more examples, but at this time the finding definite integrals, Riemann integrals, same thing, is done by indefinite integrals or antiderivatives. Okay, so then the rules of antiderivatives we had now will give us most of the time the answers in this easy fashion. So once again, look at this picture. So we have our area under the graph, the one that we started with evaluating by taking limits, and then we have, as you can see, the computation is really simple. In the even if that step might be a challenge, that step from a function to its antiderivative. It is a challenge, will be a challenge, it's always a challenge, but once you find it, it's no challenge to actually to verify the answer. Okay, so how do I find antiderivative from here to there? Well, that might be questionable. This one is easy. Okay, so once you found it, you just differentiate. You differentiate f capital, right? Look at it. X minus x cubed plus c. X derivative of x is 1, derivative of x cubed over 3 gives you x squared, c goes to 0, so and you have the answer. So at least in this sense, you are on a firm ground. You can if you are comfortable with differentiation, at least you can always verify your integration. And then it becomes really easy. Then the last step is actually simply you take your antiderivatives and evaluate it twice. Okay, substitute two values, subtract, and you have the answer 2/3. Okay, so so that's where we stand, and at the end we started also the slightly more complex example, but still manageable. The finding the area under the graph, not the area under the graph. The question is formulated as like this: simply verify that the area of the circle of radius r is pi r squared. Okay, so and then now we at least we know how to approach it. Okay, how we represent the region as the area under the graph. So all we have to do is to find the function, which we did, plug it into the equation and into our formula right here, and then what remains is simply some mechanical operation, pretty much. So the conceptual part is over, and the challenge is purely computational. And most of the time in Calculus 2 you will be asked to carry this out by hand, and so explain what is how you do it. And it's sometimes more challenging, sometimes less, but ultimately you can find a lot of the answers in the end of the book. Okay, so inside the cover and the end of the book there's a list of integrals that at the very least you should learn how to use. Okay, which is just as important to actually be able to derive those formulas. And so get this step is with nothing but the table is very useful, very useful skill. Okay, so that's what we did, and then once you have this, the rest is easy. Once again, you have your antiderivative right here. You evaluate twice, subtract. The answer is, as you can see, works out just fine. So, like I said, this will not be in Calculus 2. That will be insufficient if you need to point out how you get from point A to point B. Okay, so we'll look into that later a little bit, to making the very first step towards techniques of integration. At this time, we'll just accept it as is. Okay, so all right. So that's fine, and the practice will be in the next homework. Some integration will be asked of you, but otherwise we are gonna be there are just a couple of topics left that we have to cover, and so let me start a new one here. Okay. Where's it? Okay. Okay, so one topic is really big and goes through mathematics. It is called the change of variables. Okay, so let me go back to differentiation to just explain what it is. It is primarily the easiest example of the change of variables is the change of units. Okay, change of units. So you have your function, and you have two quantities, input and output, and they might be measured in different units. The simplest example that we started with, as you recall, x is time and y is location. That was done in the very beginning, and then you can imagine how these two things might be measured in different ways. So your time might be measured in seconds or in terms of minutes, and location might be measured in miles or maybe in centimeters. And then its measurement is important, but then actually there is a little bit more to it. And what if what also might change is the starting point. If we're talking about location, where is it's like Greenwich meridian, and you measure the distance from that meridian in particular direction, but there are others competing meridians that would be used for measuring distances. And that will produce a different function. Okay, so with time also, do we start from? I mean, even time you could measure from AD, or you can measure from whatever the everything else was, Chinese year, or creation of the world, another number that was used at some point. So so all of that might change, and the point is that how does it affect our theory? And it shouldn't. Okay, so let's and then others certainly these are just two quantities, and then you can think about temperatures in Celsius versus Fahrenheit, and you have weight in terms of pounds and kilograms and so on, and so on. No end inside of this really. And that's certainly one place where it is a mess of units is physics, and then you'd better make sure that the result of changing the units would be predictable, so the theory would be still applicable. So okay, so this is how geometrically this happens. Well, let's do it algebraically first. Okay, so say let's just to clarify. Let's look at time first, and say x is measured. There's some subtle point here. Is measured in seconds. Okay, and suppose t is measured, also time, in minutes. Okay, then, and that's the key to understanding of this, is that there is a functional relation between them. So you can express one in terms of the other. Okay, so that's the problem. Then express x in terms of t, or vice versa. Yeah, well, x in terms of t. Okay, so what is it?
T equals x over 60, or x equals 60t.
That's right. X measured in seconds will be 60 times t, where t is measured in the same amount of time is measured in minutes. So there are more seconds than minutes in the same time period, so we'll multiply. Okay, so similarly, location. Say typically we are talking about, say, feet. So y measured in feet, and say u is measured in inches. Okay, so once again I want to express, how about I express u in terms of y. So u is equal to what? No, yeah. Hold on a second, I get confused though. So, okay, so if you have 1 foot, then you have 12 inches. Okay, 12 y. Okay, great. Okay, so as you can see, then let's match these up. 1, 2, and 3. What is the relation between these three? What is the possible relation between the three? These three functions. So what do we do with them?
Combine them.
Specifically, how?
You would take either y or u variable and put it in place of the y, and then the x or t variable.
Right, yeah, so what's the word for it?
Integrate? Is that?
What? No. Substitution is a good word. There's another. The word for operation on functions, very important. So it is indeed, so we substitute. composition, yes. We substitute. So, and we could do two. I don't want to do both of them simultaneously, so I'll just do two separately. So either have u equal to 12y, y equal f of x, right? So that's one. And or if I do the other, then I have y is equal to f of x, which is 60t. So that is literally substitution. I replace y with f of x on left, and I replaced x with 60t on right. Okay, so these are the compositions. So you can put them in the form of like sequence. So from, if I want to read it from right to left, unfortunately it goes the other direction, but so I'll go right t to x to y to u. Okay, so these are the relation between the four variables. So this one is just multiply by 60. Okay, then just apply f, and here multiply by 12. Okay, and these are just two possibilities of, I picked the specific units, and that's why the relation is so specific. But generally speaking, I might have different functions. So for example, I could have x equal g of t, because the substitution could be anything. It could be instead of meter, you could have the metric system stepping into this, and then well, not for time, but maybe hours. Okay, so that would be given a different function g. Okay, and here I could have some u is equal to h of y. So another function. The point is, but we'll stick with the linear substitution. So this is so far a linear. The function f could be anything, and that's what we have been studying. But at its very simplest, the substitution is linear. And then the point being is what happens to those concepts of calculus that we have learned, beginning with naturally the velocity. So this is the relation between time and location, and then what we derive from it is the relation between the velocity and time. Okay, so then so with the same two variables, we have y equal f prime of x. Okay, so, well, I don't really, do I have it here? I still haven't found a good way to put it when there's no good name for the variable. So we keep writing this. Right? So this looks familiar. I have y equal f of x, and then I'm talking about y equal f prime of x. The f of x is a location as it was started. Just a minute. Okay. So we're talking about the location right here and time. Okay. And the problem with this is, and then we have written this many times. Unfortunately, in this setting when the units make sense, y is not the output of the new function, right? Because even though x is still time and still measured in, as we determined, in seconds, right? What is the unit of the output of f prime? So starting with y equal f of x, x is, in either case, is time measured in seconds. Y, however, was measured in, as I recall, feet. Wait a minute, feet, yes. And this one is measured in feet. Okay? What's the output of f prime? Well, what's the meaning of f prime to begin with?
Which is the derivative of
it is the derivative, yes, but if we're talking about motion.
Velocity.
It's the velocity, okay, and the velocity is measured in what units? Feet per second. Okay, so that's why I crossed it out. It's not the same y, right? So we cannot easily replace it in that manner. Okay, so either you come up with a different letter. I could certainly put like z here or something like that, so that there would be no confusion about it. It is literally, you can have two axes, two xy planes, except x is the same, but y is not the same. And remember then when we plotted the graphs of functions and its derivative, so positive, negative, positive, something like this. Okay, so the units are different, so I could put z here. That would make more sense. Just to be careful about it. Okay, so and the question then still remains. It is what does the change of variables do to our velocity? So how does f prime change as the units change? Okay, so certainly we could try just to use common sense, but let's try not to for a moment. But instead, let's do. Well, so can you tell me how mathematical address this? So in other words, so I'm changing. Let's concentrate on x first. So I'm looking at this. Okay, so then y is still the same, still measured in feet, and then but instead of fx we have 60 f of 60t. Okay, so two new variables, and then well actually maybe it would make sense then. To see what we're comparing. So that notation f prime does not tell us. So we could, I mean, it's obvious that we're talking about, but what we really want to talk about is this df, or let's put it this way, dy dx versus dy dt. Okay? So y is the output variable of our location function as a function of time, except we have two. Now, y depends on x, and y depends on t as well. So this is where we are, right here. Starting with either we start with x and go straight to y, or we start with t, and then in two steps we get to y. Okay, so so that's the relation we need to figure out. And so what do we do? You remember what the relation between the two? They are proportional, that's right. Can you justify it in any way?
Proportional by a multiple of 60.
Yes. How do you justify it?
With the equations?
Well, we'll get to equations inevitably, so if you want to use the equations, sure, or any other word. Can maybe common sense, does common sense really tell you that it is indeed supposed to be just multiplied by 60? Okay, so if let's see, so there are more. What has happened is we switched from minutes to seconds. So then naturally if you switch from seconds to minutes, you cover less per unit, not more, right? So you don't multiply by 60, divide by 60. Okay, yeah, that kind of makes sense. To make sense, it's more in a more consistent way. I would like to invoke something, and that is what is the relation between these two mathematically. If you remember, the diagram. Oops, what happened here? The diagram above the top. What does it? I mean, we already have the right word here. And the right word is this. We're talking about compositions, right? So that's the composition that we are going from t to x to y. That's the composition we're talking about. And at the same time, we are interested in the derivative. So compositions, derivatives. What is this about? Composition of derivatives. What's the name of it? Of the topic? Or tool? Theorem? Rule? Remember the name? The chain rule. Yes. Okay. So it's about the chain rule, and that it will clear things up, and it is really fairly straightforward if you try. So we have three variables, t, x, and y, and they are related to and there are three derivatives, right? From x to y, from t to x, and from t to y. Okay. So here we only have two. So there's the third one, which is what is it? Dx dt. Okay, so we'll put it in, but let's just write the chain rule, which is we take the composition, the bigger one, which is dy dt. So if you go all the way through from t to y, that's your derivative. And remember what's equal to? Very convenient Leibniz notation. So things kind of cancel out. Remember the formula? Well, there will be dy dx, the other one, multiplied by well, you can see the dy is in the numerator, so that's okay. But then we have dx instead of dt in the denominator. So we got to get rid of dx, and we have to have dx dt, right? So that way you can do this symbolically in the back of your mind and realize that you have the formula correct. So then we have what is dx dt? We actually can be specific because it's right there at the top. This is function g, as a matter of fact. It doesn't matter. We have a specific function. So what is it? It will be dy dx times $60. Okay, and then this is old, and this is new. Yes. So dy dx is the old, and this is new. So as you can see, then what happens to how do you produce the new one from the old? You multiply by 60. Wait a minute. I was making a point that it was supposed to divide. Hold on a second. Okay. So once again, we have more units per unit of time. So it was measured in seconds. Now it's measured in minutes. So we have from t2 multiplied by 60, and then so if our velocity was measured per second, then no, it is multiplication by 60, right? Because we are going not from minutes to seconds, we're going from seconds to minutes, which means that per minute there you cover longer distance. So it does grow, and so you multiply by 60. Sorry for confusion, but that's in any doubt. when you do algebra, you probably will be okay. Okay, so as long as you remember which one is new, which one is old. So as you can see, so the conclusion is, I suppose, so multiply the old velocity by 60. Okay. What about acceleration? If you want to guess. Just guess. What?
Is it just taking the derivative again?
Yeah, the acceleration is the derivative of the velocity. Yes, but if you can guess what it does to the change of units, what does it do to acceleration? So it's second derivative. The first derivative required multiplication by 60. So
Just another multiplication by
another multiplication by 60. So it will be 60 squared, 3600. Okay, so then it does grow, but even more than the original. Okay, so but in general, as you can see, we could have any change of variables for what is being underlined there in blue is the change of the input variable, and it causes multiplication by whatever it causes the derivative to be multiplied by the same number as the substitution formula. So that's the substitution formula as we switch from minutes to seconds. Okay. Okay. So let's, and then there's a totally different story. Now, if we switch to this, so now we change of variables in the output. So not time, but distance. So fortunately, the tool is the same, but the result will be quite a bit different. So let's guess again. So this is we're looking at what's on the left rather than what's on the right. So this is what we're looking at. Okay. So as you can see, we're multiplying the variable by 12. So why by 12? So that is clear, just a substitution. So that we're not really concerned with that part. We already know. We just replace. You have all functions that you might be studying, and then you're switching from feet to inches. What do? You replace each. You substitute. Well, actually, the substitution is elsewhere. It is the substitution would be replacing y with y over y is u over 12. Okay, so that if you want a substitution, that would be substitution, right? So if you have y there somewhere, then it is replaced with u over 12. Okay, and that's how you switch from feet to inches. Okay, now, but what the actual question is, what does it do to the velocity? So velocity now is measured not in feet, but in inches. So common sense, what does it tell you about what happens to the velocity? Once again, it's up or down, pretty much. We already guessed that it must be simply multiplication. So which way do we multiply or divide? You multiply by 12. Let's see. So we cover more inches per the same period of time. We cover more inches than feet. So we multiply by 12. Okay. So that is the answer that we anticipate. Let's carry it out with the chain rule now. Okay. So the chain rule, naturally, the formula is the same, except, yeah?
For the chain rule for the first part, when you divide by 60, not multiplying.
What?
When you go from minutes to seconds, say I'm walking down a hallway, I'll get farther in 1 minute than I would in 1 second.
Hold on a second. Per minute, right, so multiply. We did multiply. Remember, we corrected ourselves. We did multiply by 6. So per minute, which is the, no, wait a minute, we're switching from seconds to minutes. Yes, from seconds to minutes. So we sort of have more time. Per unit of time, we have now more time and we cover more, right? Make sense?
I think we just might have it backwards.
Well, let's think again. So okay, let's take a minute. So we'll set algebra aside, and so I cover 5 feet per second. Originally, 5 feet per second. Okay. Now per minute.
It would be more.
Yeah, 5 but by 60. Yeah.
But in the equation, are we going from minutes to seconds?
You're not talking about the derivative. You're talking about this formula.
No, the one down there.
This one. So yeah, that's what. That's right. So the old is less because it's measured in seconds. So these are seconds, and these are minutes. Right. So dy dx was measured in seconds, and now it's now measured in minutes, and we cover more distance per unit. Right? It's, yeah, it is a bit confusing, I know. From the top of my head, I cannot tell which one's supposed to go. And the confusion is especially when you have to consider both of them. So on two ends of the function.
Well, the way I thought about it is if t is 1, then x would be 1 over 60, wouldn't it?
If t is 1, so how that would be per minute. Per minute. And yeah, it will be 60 as per second. Multiplied by 60 is the speed per second. So the algebra doesn't lie. So if in any doubt, just trust your algebra and then just see if it makes sense. Another option is, yeah, common sense is just to verify that if you're really in doubt and you're not sure. So let's do what we have time left to carry out the other end. So the same formula. So chain rules remains the same. So let me rewrite. Well, it's not the same. The units, the variables are the same. So I'm looking at what underlined in green. So I will be looking at du dx. Okay, du dx is in terms of the other two. Okay, so du dx is what? So the product of the two other derivatives. So it will be du dy times, once again missing term, just like over there.
12.
What?
12.
No, I'm just writing the chain rule for those variables. Look at that cancellation that we are seeking in order for the terms to match. Dy over dx, yes. Okay, so once again, this is why it works. And now, so once again, let's u is u is measured in, that's the new unit, and it is measured in inches. So this is inches, and while the one that we're going to end up with is that's y, it's measured in feet. Okay, so so du dy is unknown function that we don't study. We just want to keep it. And now dy dx, looking at the formula, dy dx. So that formula in pink actually is what helps. Hold on. Do we divide by 12?
I think we should just replace the u and the y in our location. So u is measured in feet and y is measured in inches.
No, let's hold on. Y is measured in feet, yes. Well, u measured in inches. Okay. So the relation there and let's confirm that circled thing over
I
there.
think we have 1 inch equals 12 feet.
Really? No, hold on a second. So if we measure the same distance, so if y is measured in feet, and suppose it is 1 foot, then we get on the left, we get u, the number of inches, which will be 12. Looks fine to me.
In the pink,
Yeah.
it says 1 foot is 1/12 inch.
Well, no, it's the same formula. These two formulas are the same. U is equal to 12y, or y is equal to u over 12. It's the same thing, right?
But shouldn't 1 foot equal 12 inches? It says 1 inch equal.
We're not saying that u is not a foot and y is not a foot and u is not an inch. It is u is the number of inches, and y is the number of feet. Okay, so there is this subtle difference, and also it's very easy to get confused. Try to exchange dollars for pounds and pounds for euros. Yeah, good luck. So it's about the same problem. Yeah, and it is confusing. So it's the formula they multiply when you cannot multiply a pound by anything and get a dollar. It's not going to happen. You multiply the number of dollars that you have, which could be 1, and then you will get the number of pounds by some coefficient. Okay, so that's the formula. Then once again, it's not it's not one unit equal to the other unit. It's how many units we have, which gives you the opposite relation. Where you had multiplication, converting 1 foot is equal to 12 inches, but the number of feet, which will be then divided by 12. Divided by 12 gives you a number of inches. Okay, so then the dy dx is, according to this, I'm sorry, where's d? It's not dy. Hold on a second. Why dy dx? It's not dy dx. Du dx, du dy, no, it is correct. Okay, no, the first term is this one is gone. This is where it is du dy, which is 12, right, times dy dx, which we keep, right, just like above. It's the same thing. It's the same thing. This one is the one that we're not studying. We're just looking at it. Okay, so and that's so it's 12. Multiply by 12. Okay, we'll finish it next time.